Hey guys, this is Pratik from IoT Bits, and this time we have some PWM control LED circuit here, and it's based around the AMC7135 constant current sync. It is a very low cost 3-pin device, and you can actually use it to control the brightness of the LED as well using PWM signals. But the problem with this setup is that the datasheet of the AMC7135 does not specify what kind of signals it can actually take and what is the maximum frequency it can actually operate on. So when you don't know those specifications, it's very difficult to design a circuit to drive the PWM at proper frequencies such that the current sink can actually respond to the changes of the PWM signal. So what we have done here to test the capabilities of the AMC 7135 in case of handling PWM signals is that we have hooked our entire setup up to with the oscilloscope, and what we have done is that added a shunt resistor here in series with the LED to find out whether the current sink is actually responding fast enough to the PWM input signals. So let's head over to the pen and paper stuff and find out what exactly we're doing here. So coming back to the pen and paper stuff now, we have the battery connected right here. It's the lithium polymer battery, so you'd typically expect the voltage of that battery to be around 4.2 volts in open circuit mode, and even under loads this actually doesn't really drop down below 4.2 volts. So if your battery is fully charged, then this is pretty much what you'll find across that, and with that is connected in series the current sink. This can actually sink 350 milliamps for any voltage that is between 2.7 to 6 volts according to the datasheet, and I've linked in the datasheet down below in the description, so you might want to take a look at that. And as for this capacitor, this is not specified in the schematic, but you need to place that because if you're sending in PWM signals, this entire current path is actually going to connect and disconnect quite a lot of times, and as a result, if the rising edge is quite fast, you can actually get a lot of EMI interference, and that's not something that you want. So it would be a safe idea to place something like that here. Well, you actually don't have to place a capacitor here as shown in the example schematic in the datasheet, because this will actually sink in the PWM signals and you won't really be able to get an effective PWM control on this. So that's not something that is recommended. And by the way, you might be wondering why I actually placed the current sense resistance down here. The problem is that actually when you're trying to probe signals off with an oscilloscope, the thing is that all the ground pins of an oscilloscope are sorted, which means that if your signal generator is actually feeding signal in here, then that ground reference and your oscilloscope test probes ground reference are all going to be shorted. So if you actually have this 1 ohm resistor over there, the problem is that when you're trying to probe the voltage drop across the resistor here, what will happen is that the ground pin of the oscilloscope signal input is actually going to short out directly to the ground. What will happen is that will actually connect the entire 4.2 volt battery directly to the LED, and most probably it will actually destroy that, because the lithium polymer cell can actually discharge a much larger current than just 350 milliamps. So that's the reason we actually had to place the 1 ohm shunt resistance down here. And so we're actually going to probe this channel, and we're also going to probe this channel. What we'll do is we'll make a comparison to see whether the trend on this channel is actually following this. So what should happen is that we should see the PWM rising edge and the falling edge here in a very square wave manner, because the thing is that this signal is actually rising and falling pretty sharp because it's coming from the function generator, but the channel 1 or the current trend is actually going to follow it rather slowly. So we should see something like this and something like that. So this finite rise time on the current sink part of things actually tend to limit the minimum duty cycle that you can actually achieve when trying to bring this PWM duty to a very minimum. So what happens is that when you actually reduce the PWM cycle to something very low, the rise time is not going to meet the upper edge of the current sink, and the problem will be that you won't really be effectively getting maximum power across the LED based on the PWM duty. So it's actually going to cause some jitters in the output intensity, and people are actually going to notice that. So the purpose of this entire thing is that we need to find out what is the minimum time period that we need to have so that it actually does not really flicker when the brightness of the LED is very low. So now let's head over to the oscilloscope and see the kind of waveform that we are getting out of this setup. Okay, so here we are on the oscilloscope and the entire test setup has been connected. You can see the duty cycle of the function generator changing here. So the duty is mentioned here and it's directly being fed down to the LED driver circuit. So we're going to vary this, and we're actually going to see how the current of the current sink actually follows the PWM input, and if it is extremely slow, then we'd know that cannot exceed that particular frequency here. So let's head over to the oscilloscope part and see what happens. Well, as you can see here, so the blue trace is actually following the function generator output because this is a clean rectangular wave, but the yellow trace is actually following the current sink as it is actually trying to draw 350 milliamps based on this pulse width. So let's match the traces here. Okay, so zooming in, well, the problem here, as you can see, is that the PWM signal input is strictly rising and strictly falling, but this thing actually rises slowly and it takes some time to stabilize. It's even going down to the negative with an undershoot. So you need to take that into consideration, and if you actually touch the duty such that the duty is lowered, you get this problem. What happens is that the current sink is actually being turned off before it even reaches a stable level. So this is something that can actually cause jitter in your lighting, and you don't really want that. So you just need to have a minimum duty cycle of about, here it's about 2 divisions, which is slightly around, it's going to be around 10 microseconds. So what you get to see from here is that with the AMC7135, if you actually reduce the on time to under 10 microseconds, you're actually going to get some jitter in the lighting. This is something that you need to take care of because it actually causes very drastic drop in the lighting intensity, and that's not something that you want because people are actually going to see that. So I hope this helped you. If you're using the AMC7135, then this information actually really matters when designing lighting systems that are actually capable of going down to very low intensity levels. If you need the screenshots to have a detailed look at this, then please head over to the description and you will find some links to an article that will actually show you the screenshot that you are seeing now, and you can actually get a better idea of what frequency is suitable for driving this thing. Also, if you want some ideas or circuit design or even firmware or specific AT commands based on the ESP8266 or ESP32, then head over to the IoT Bits website. We have a premium section there and we can actually help you design your IoT applications. I hope this was useful for you, and I'll catch you in the next video. Thanks for watching.